On the reinforced concrete columns, we are going to solve some additional problems related to the mentioned subject. To start with, based from the problem, according to the Simplified Reinforced Concrete Design, second edition by Engineer Mark Jefferson B. Castro, a 450 millimeters by 450 millimeter concrete tied column, which is not braced against side sway. It has an unsupported length of 5 meters. Assume an effective length factor of 1.3 using the specified compressive strength of concrete of 27.6 megapascal and the yield strength of steel reinforcement of 415 megapascal. A first-order analysis has resulted in the following factored loads and moments. So for the sake of this problem, we are going to use the radius of gyration of 0.30 of the edge or the one side dimension of the column. The following are given: factored load at a given eccentricity or PU of 2,400 kilonewtons, a end moment, factor end moment, this is end, this is E, factor end moment on compression member at the end due to the loads that causes no appreciable side sway or M sub 2 and S or no appreciable side sway or NS means no appreciable side sway over 132 kilonewtons meter factored end moment on compression member at the end due to loads that cause appreciable side sway or causes appreciable side sway or M sub 2S of 122 kilonewton meter. The sum of factored axial loads for all columns on the floor or the summation of the factored axial loads is 72,000 kilonewtons and sum of the critical load for all columns on the floor or the summation of P sub C is 214,000 kilonewtons. Determine the following. First, the moment magnification factor for frames not braced against side sway, and determine the magnified factored moment due to the base or due to be used for the design of the column. Okay, on this slide, as we can see the section of the said tied column. So it is a square tied column having a dimension of 450 millimeters by 450, and it has a 8 it has it has 8 8 pieces of 32 millimeter diameter bars, and the effective concrete cover of the steel reinforcement to the extreme concrete fiber is 60 millimeters on center of the reinforcement. First, on this type of problem, we have going first to determine if the section is a short column or a long column, or in short, we have first to check the slenderness of the section. For the solution, as I've said, check the slenderness effect for columns not braced against side sway. So for this type of problem, it is also already mentioned that it's not braced against side sway or sway frames on the other term. Okay, if KLU over R or is less than or equals to 22, there is no need to consider the slenderness effect of this section. However, if the KLU over R or the slenderness ratio is greater than compared to 22, we should consider the slenderness effect of the section. Okay, As stated in the given, effective length factor of K is 1.3, then supported length of 5,000, and the radius of gyration of 0.30 of the one side dimension of the square tiled column, we have 48.148 as a slenderness ratio of the section. So as we can see, as we compared it to this criteria, it is observed that 48.148 is greater than 222. Therefore, we should consider the slenderness effect on this type of problem. So in short, this type of problem is a long column problem, and we have to consider its slenderness effect. Next, or the actual questions we are asked is determine the moment magnification factor for frames that brace against side sway. Okay, so for this type of non-brace against side sway problem, the moment magnification factor has an equation of 1 over 1 minus the summation of the factored axial load over the 0.75 or 75% of the summation of PC or summation of critical loads for columns on the floor. Okay, for the moment magnification factor for frames that brace against side sway, all of the given are already presented on the question or the um, stated problem. So we're going to substitute it to determine the moment magnification factors. Okay. After we substitute the given values, 1 over 1 minus 72,000 as the summation of factored action loads for all columns of 72,000 and 0.75 of 214,000 or the sum of the critical loads. Okay, after substituting and computing this in our calculator, we get the moment magnification factor for frames that brace against side sway amounting to 1.814 um, 1.814. Okay, as mentioned in our handouts, the moment magnification factor should be at least greater than or equal to 1. Okay, as computed, the moment magnification factor yields to 1.814, so it is greater than 1. So we are true to the condition. However, if hypothetically this moment magnification factor yields to less than 1.0, okay, we're going to use the value of 1 as a moment of magnification factor. Okay, again, if the answer on this equation yields to less than 1.0, we're going to use the value of 1 instead for its moment magnification factor. Okay, so for the answer, for the moment magnification factor for frames that brace against side sway, we have 1.814. Letter B, for the magnified factored moment to be used for the design of column, so M2 stands for the larger moment of on the end of the column. Okay, for the magnified factor moment, we have equation m sub 2 is equals to the m2 no noticeable or no appreciable side sway or m sub 2ns plus the magnification factor multiplied by the moment um, in reference to the with appreciable side sway or m sub 2s. Okay, so as stated, most of the givens are already on the given problem as okay from S sub 2 and S and M sub 2S. And this moment magnification factor is the previously computed uh, value in reference to question letter A. Okay, so since the given are already gathered and um, recorded. So we're going to substitute um, those given values. Okay, we have magnified factor moment to be used for the design of column. We have 132 kilonewton meter of M sub 2ns or non-noticeable side sway plus the moment magnification factor of 1.814 and the moment cause or due to the cause of noticeable or appreciable side sway or M sub 2s. So after substituting these given values, our answer or the moment to be used for the design of column should be 353.308 kilonewtons per meter. So this is the moment to be used in our design for column for this specific problem. Second problem, we have a tied column of 510 by 510 millimeter tied column or square column is reinforced with 12 pieces of bars having a steel area of 700 square meter per bar. So each bar has a at least 700 square millimeter area. Okay, and that is 12 pieces. The column is subjected to a factored moments without causing side sway. Okay, take note of this, without causing side sway. M sub 1 or moment 1 is 660 kilonewton and M2 or the larger moment is 680 kilonewtons meter. It carries an ultimate axial load of 1,800 kilonewtons. Okay, and the column has an unsupported height or length of 4 meters. The modulus of elasticity of steel is 200,000 megapascal. The specified compressive strength of concrete is 20.7 megapascal. And the creep factor or the beta sub DNS is 0.40. And the effective length factor for this problem is 1.0. Determine the following. Compute the relative stiffness of the column considering moment of inertia of reinforcement about the centroidal axis of member cross-section, or we're going to consider the ISE or the moment of inertia caused by the reinforcements. Letter B, compute the moment magnifier factor if the column is bent a single curvature. So single curvature, that means the ratio of the smaller moment in relation to the larger moment should be in terms of a negative value, since it is stated that it is a single curvature type of problem. Next, compute the design moment of the column. So as we can see on this other side of the slide is the dimension and the illustration of the square tied column. So as we observe, um, the center of gravity of the section is exactly at the center of this section. Okay, and having a distances from the top bar of 200 millimeter to the center of gravity and 100 millimeter from the middle reinforcement to the center of gravity. So those centroidal distances are equal. So from this 200 and this one also is 100 millimeters. For the solution, or letter A, relative stiffness, or EI effective considering the area of steel reinforcements. So since as stated that we're going to compute the relative stiffness considering the area of reinforcement, we have equation of 0.20 modulus of elasticity of concrete for or EC, IG of or the gross moment of inertia plus the modulus of elasticity of steel or E sub S and IS or the ISE or some references in relation to the steel reinforcement moment of inertia over 1 plus the creep factor or beta DNS. So in order for us to solve this problem, we have first compute the individual values of the given um, parameters such as the E sub C or the modulus of elasticity of concrete, moment of inertia of the gross, etc. Okay, first, we have first to compute the modulus of elasticity of concrete. We have 4,700 squared of F prime C, or F prime C is the specified compressive strength of concrete. After substituting those values, we have 21,383.709 megapascal for the modulus of elasticity of concrete. Next, for the gross moment of inertia, we have, since it is a rectangular or square section, we have a gross moment of inertia of BH cubed over 12. So luckily, it is a square column, so there's no need to consider which side is needed to be raised into 3 or raised to be cube. Okay. However, if the section is, let's say, rectangular, the larger value should be in raised to 3. Okay. For the sake of this problem, since we have a square section, there's no need to consider which is the larger or which value that needs to be raised to 3. Okay? Base of 510 and 510 at the height raised to 3 over 12, we have 5,637.67 times 10 raised to 6 millimeter raised to 4 for the gross moment of inertia of the section. Next, for the ISC, or the moment of inertia caused by the steel reinforcement, okay, or 8 pieces. So 8 pieces of 700 square millimeter per piece times 200 squared plus 4,700, or 4 times 700 times 100 squared, or 252 times 10 raised to 6 millimeter raised to 4. So the value of 8 came to this equation. We have 1, 2, 3, 4, 5, 6, 7, 8. So 8 pieces of 700 square millimeter each bar, and we're going to moment it to the center of gravity. So 8 times 700, so 8 again, 1, 2, 3, 4, 5, 6, 7, 8. And the distances to the center of gravity is equals to 200. Next, 4 pieces of 700 times 100, we have 1, 2, 3, 4. Top, then 700 square millimeter each bar, and distance from the center of gravity is equals to 100. Okay, so this value came from the discussed um, previously. So 8 pieces of the bar, 700 square millimeter per piece, and their square distance, we are 200 millimeter. So 4 pieces, 700 square meter per piece, and then 100 millimeter for its square distance. So that is the origin of this value. 8 pieces of bar. This is the individual square millimeter of each bar, and the square distance from the center of gravity. So if we compute this equation, we have 252 times 10 raised to 6 millimeter raised to 4 for the moment of inertia caused by the steel reinforcement. Okay, and BDNS, and as it is already given, of 0.4, we now going to substitute those values to this equation. 0.20 ECIG plus ESIS or ISE plus 1 plus the creep factor. So after substituting those intended values, we have the relative stiffness of 53,222.276 times 10 raised to 9. That is Newton millimeter square. So we have Newton Newton millimeter squared. Okay. So that is the relative stiffness considering the area of steel reinforcement. Next, letter B, for the moment magnification factor for frames not braced against side sway or sway frames, we have equation of Cm over 1 minus Pu over 0.75 Pc. Okay, so for the value of Cm, we have the equation of 0.60 plus zero point 0.4 of the m1 over m2, or the smaller moment over the larger moment. Okay, so one thing that we need to consider, since it is stated that it is a single curvature, so this ratio should be taken into a negative. So after substituting 0.60 plus zero point 0.4, quantity 660 divided by 680, since it is negative, so we have the value of Cm of 0.988. Next, for the value of PC, or the critical buckling load, we have pi squared EI effective, or the relative stiffness, over the KLU squared. So substituting EI effective, which is the previously computed value of 53,222.276 times 10 raised to 6, and the effective length factor of 1.0, and the unsupported length of 4,000 is squared. So we have the critical buckling load of 32,830.176 kilonewtons. Okay, so after we compute the value of Cm and Pc, and since P is already given, so we have to substitute these values to this equation. Cm 1 plus or 1 minus Pu 4.75 of Pc. We have moment magnification factor of 1.066. Okay, this is the multiplier factor for the moment needed for the design of the column. Plus, the design moment of the column, or the MC, is the moment magnification factor multiplied by the larger moment. 1.066 times 680, we have 724.88 kilonewtons meter. So this moment will be used for the design of the column. Next problem, we have problem 160. A tied column 350 millimeters by 600 millimeter in a cross-sectional area, or in a cross-section, is reinforced with 6 pieces of 28 millimeter diameter bars, arranged as shown in the figure. So this is the arrangement of the section as well as their reinforcement. Let us assume that the column section has a strain on each edge, or the compression side, assuming this is the compression side, equal to 0.003, and has a tensile strain of 0.002 on its outer side. So this is assuming this is the compression side, this one is the tension side, okay, with their corresponding strain. So on this type of problem, we're considering the strain caused by the loads on the column section. The specified compressive strength of concrete is 27.6 megapascal, and the yield strength of steel reinforcement of 414 megapascal. Determine the total compressive force of the steel reinforcement considering that it is reduced by 0.85 of F prime C to account the holes of the concrete. So in order for us to consider the hole produced by the reinforcement, we have to reduce our strength to 0.85% of F prime C to consider the holes of the concrete. Letter B, determine the nominal axial load that causes the strain distribution in the column section. And letter C, determine the nominal moment that causes the strain distribution in the section. So this is the cross section with 6 pieces of 28 millimeter diameter of RSB, or reinforcing steel bar, and their effective concrete cover of 62.5 millimeters. For the solution, or question letter A, we are going to illustrate the stress or strain diagram in relation to the given values. So as stated, assuming this is the compression side, we have a strain of 0.003. This is 0.003. Sorry for the sum of the erasure. Okay. For the compression side, 0.003 of the strain, and for the tension side, we have 0.002. Okay, after projecting the outer edge of this section and their reinforcing steel bar, this is the strain of steel reinforcement for the tension side and the strain of steel reinforcement on the compression side. Okay, after since the strain is in terms of a triangular diagram, we project these values to this and connect those points and wheel to this kind of illustration. Okay, so the value of C, as we review the previous discussion for the design of lectural members or column, the C is the distance on the outer side to the center of the um, section due to the strain. Okay, so assuming this value is C, or the distance from the neutral axis from the extreme compression member, okay, we're easily going to solve the value of C by ratio and proportion, given that 0.003 for this triangle, this larger triangle over C, okay, and 0.02 and 600 minus C, this is 600, and this one is C, so this value is 600 minus C. Okay, after substituting this equation in our calculator, we have the value of the C, or the distance from the neutral axis, of 360 millimeters. Okay, this one is 360, and the difference between 600 minus C is 240 millimeters. So in order for us to easily solve this problem, we have first identify what is the value of C, or the distance from the neutral axis. Okay, later on we're going to use this. Okay. Next, next thing we need to compute is the strain caused by the steel reinforcement at the tension side and the compression side. So again, using similar triangle, we have the strain of steel reinforcement on the tension side over 177.5 for the distances that easily computed, easily easily or easy to compute. Okay, versus the 0.002 of strain on the outer side over 240, the difference between 600 minus C. After substituting those values, we have 0.001479 of the strain on the tension reinforcement. Next, strain caused by steel reinforcement on the compression side. So again, trying a similar triangle method, this strain over 297.5 is equals to 0.003 over 360. So we have the strain of steel reinforcement has a value of 0.002479. Okay, so after we compute the value of the various strains of the steel reinforcement for the tension and the compression side, we're going to identify it further if it is tension reinforcement tension still will yield on the tension side and compression still will yield on the compression side. First, we have to compute the value of the strain of yield strain or E strain at Y or Fy. Okay, Fy is over Es of so for the strain that we're going to compare with the given strain for tension reinforcement, the decompression reinforcement is 0.002073. So this is the value that we're going to compare with for this given value in order for us to identify if the tension reinforcement will yield and compression steel reinforcement will yield or not. Okay, so since EY is 0.002073, it is greater than the value of steel reinforcement strain for the tension reinforcement, or in short, EY is greater than ES, we can say that tension steel will not yield. So in short, um, strain of steel reinforcement at the tension side is smaller compared to the strain at Y. Next, however, since strain at Y or caused by Fy is less than strain at S, this one is S, yes, or compression reinforcement, therefore compression still will yield. Okay, or in short, we can say that for tension side, Ts or Fs is not equal to Fy. And this one we have F prime S is equal to Fy due to this condition. Okay, this one is equal. To account the holes in concrete, so as stated, we have to minus the consideration for the hole of 0.85 f prime c, depending on the given problem on how many percent or equation need to be considered for the holes on the section. For the sake of this problem, as stated, that to account the holes in concrete, we have to consider the steel reinforcement, the compression side should be minus to the 85% of the F prime C. So after to satisfy the given condition or to account the holes in concrete, we substitute the value of Fy and the 0.85 of F prime C given the value of 391.14 megapascal. Okay, for the compression force or C sub C prime S is F prime S multiplied by the area of concrete reinforcement. Okay, or the compression caused by the compression reinforcement. So F prime S times A prime S or the area of steel compression reinforcement 391.14 0.25 pi times 3 times 28 squared, we have 722.535.90 newtons or 722.35 kilo newtons. And for the nominal, okay, for the value of, wait, yes, 391.14, this Fs in consideration for the holes of concrete times the how many bars on the compression side of which is 3 pieces. Okay, after substituting, we have the total compression force on the compression side is to 722.535 kilonewtons. Letter B, the nominal axial load that causes strain distribution. So expanding the illustration on the given, after this strain diagram, we have the um, stress diagram. So tension reinforcement, we have T for the tension, compression due to concrete, and the compression due to steel reinforcement, which is previously computed, and the P or the load um, causes the strain distribution. Okay, it is acting to the center of gravity of the section or to the middle of the section, which is 300 millimeters. In order for us to compute the intensity or the magnitude of the compression block, we have first to compute the compression block or the beta 1C or 0.85 times 360 or 306 millimeters. So this value is 306 millimeters. Next, for the individual compression and tension forces, first, due to concrete, we have 0.85 F prime C or AB or the area of concrete block. We have 0.85 times 27.6 times 306 of the depth of the compression block, and the base is 350. Given that after substituting the equation, we have 2,512.566 kilonewtons. Next, for the value of the compression due to the compression reinforcement, as previously computed from question letter A, we have 722.54 kilonewtons. And lastly, for the tension force is AS or the area of tension reinforcement Fs, since tension still will not yield, so we have to take into account the actual value of Fs or the strain of tension reinforcement multiplied by the modulus of elasticity of the steel, since as I've said, it is tension still will not yield, or Fs is not equal to Fy in short. To substitute this value, we have 0.25 pi times 3 pieces of 28 millimeter diameter bar squared times the strain of tension strain is 0.001479, which is previously computed, this value, and multiplied by the modulus of elasticity of steel of 200,000 megapascal. After substituting those values in our calculator, we have 546.418 kilonewtons. For the question, nominal axial load caused by the strain, what is the value of P in short? Okay. After computing the value of compression due to concrete, due to steel reinforcement, and the tension force, we're going to equate and take a summation forces. Okay, so up and down or the sign convention should be taken into consideration. Okay, summation forces for nominal axial load that causes strain distribution, or we have the blow up of the section. Summation of forces vertical after the, as a recap, compression due to concrete is 2,512.566 kilonewtons. Compression steel reinforcement force is 722.54 kilonewtons, and tension force of 546.418 kilonewtons. So again, after summation forces of vertical, we have T plus P minus CC minus CS, or after substituting this value, we have the axial load that causes strain distribution of 2,688.688 kilonewtons. Last, determine the nominal moment that causes this strain distribution in the section. So for this equation, we're going to moment on this center. Okay, since it is the centroid. So moment acting on the center of gravity of the section. The nominal moment or the T moment arm to this point is 237.5. So this is the value of T. And CC or CS is situation having a moment of 237.5. And the CC or this is CS. This one is CC of 2000 or the value of the CC is this and its moment minus 147. We have 670.724 kilonewtons for the nominal moment that causes the strain distribution in the section.